You know that feeling, right? When you're trying to grapple with something really complex, and instead of getting clarity, you just keep getting more stuff thrown at you, more information, more data. Or um, maybe you've got this tricky problem, and the default solution always seems to be, well, let's just throw more resources at it, just scale it up, make it bigger. No. It kind of feels like trying to get a sharper photo by just adding more and more pixels, even if, half those new pixels are just blurry or don't add anything useful. You're boosting the quantity, sure, but not necessarily the quality of what you're actually seeing. Well, funny enough, this mirrors a huge trend we've been seeing in artificial intelligence for a while now. I mean, for years, the big headlines, the main story, it's all been about AI models getting exponentially bigger, neural networks scaling to these, frankly, unimaginable sizes, and the data sets. Absolutely colossal. It's really been the dominant strategy, almost a mantra. More data, larger models equals better performance. But what if that whole approach, that conventional wisdom, is actually starting to hit some serious walls?
What if the real breakthrough, the next big leap, isn't about just endlessly scaling up? What if it's about sensing smarter? Like, what if instead of just trying to process these ever-growing mountains of raw data, we could actually improve the quality, the relevance of that data before it even gets to the AI's processing core? Okay, so let's unpack this a bit. Today, on the deep dive, our mission is to really dig into this fascinating and I think pretty insightful research paper. It's titled, AI Should Sense Better, Not Just Scale Bigger, Adaptive Sensing as a Paradigm Shift. We're going to explore exactly why the current ways of doing AI might be running into some pretty serious, maybe even unsustainable limits. And crucially, we'll look at how this new idea, inspired by biology called adaptive sensing, could fundamentally change how AI perceives and interacts with the world. The promise is it could make AI, well, more sustainable, potentially a lot more equitable, and much, much more robust when it actually faces the real world. So yeah, our main source today is this paper. It's dense, definitely, but really packed with some surprising stuff and compelling arguments.
So let's maybe start by setting the scene. The current AI world, the one this paper is kind of pushing back against. When you think about the big AI news lately, the advancements grabbing headlines, what comes to mind? For most of us, I bet it's, the huge language models, the GPTs, the things powering chatbots, or maybe those massive image databases used for training computer vision. Everything built on these increasingly complex neural networks. It really feels like the whole field, for a good while now, has been driven by what this paper calls a model-centric paradigm. Yeah, the main strategy, as the paper lays out pretty clearly, has been almost laser focused on one thing, scaling up neural models, making them bigger and bigger, and constantly feeding them more and more training data. The goal, better generalization, more robustness. It's been seen as like the formula for AI success. And the logic feels kind of simple, right? If you want smarter AI, give it more to learn from more data and a bigger brain, a larger model to process it all. But, okay, here's where it gets really interesting and honestly a little bit worrying. This approach, which seems so successful on the surface, is starting to run into some very real, very fundamental problems.
You've set that up perfectly. And while, yes, this model-centric scaling has given us some truly impressive performance leaps in many areas, it's also, as the paper meticulously documents, creating some significant and frankly unsustainable challenges. And these aren't just, abstract technical issues for researchers. They have very real, tangible consequences for our environment, for society, for equity, and maybe even for the future direction of AI itself. The paper points out several key limitations, and they're definitely worth digging into. First off, and maybe the most stark, is the environmental and computational cost. It's just enormous. These modern AI models, especially the huge language models you mentioned, GPT-3 and its successors, and these complex multimodal models, they require absolutely staggering amounts of computational power just for the initial training phase. Let's use the paper's example to make it concrete. Training GPT-3 alone needed about 1.287 gigawatt hours of electricity.
Wow, gigawatt hours, that sounds like a lot.
It is. To put it in perspective, that's roughly the same amount of energy over 120 average American homes use in an entire year.
Just for training one model.
Just for training one model, one time. And that energy use translates to about 552 tons of CO2 emissions. Now, 552 tons of CO2. The paper compares that to driving a regular passenger car for more than 1 million kilometers. That's, over 620,000 miles?
1 million kilometers
Yeah.
from one training run. That's mind-boggling. It really paints a stark picture of the footprint here.
It does. And this isn't just a one-off problem. The trend is towards even larger, even more complex models. So these costs are just escalating exponentially, really. This trajectory, honestly, poses really significant sustainability challenges for AI development on a global scale. I just can't keep going like this indefinitely.
Yeah, that million-kilometer comparison really hits home. You have to wonder about the long-term planetary impact if that's the direction we keep pushing. It just doesn't feel sustainable, does it?
It doesn't. And that leads us straight into the second major limitation the paper highlights: accessibility and inequity. Because training and even just running these state-of-the-art models demands such immense computational resources, access to the cutting edge of AI development is becoming increasingly concentrated. It's mostly limited to, a handful of players with incredibly deep pockets and massive computing infrastructure.
Yeah.
The big tech companies, maybe some very well-funded university labs, large corporate research divisions.
Right, not exactly your average startup or university department.
Exactly. This centralization of power and capability effectively widens the global digital divide. It tends to benefit already wealthy institutions and nations. And at the same time, it severely limits the ability of smaller researchers, innovative startups, or groups in less economically advantaged regions to really participate meaningfully in developing this frontier AI. So the consequence is the diversity of ideas, the range of perspectives shaping AI, and maybe most importantly, the equitable distribution of AI's benefits. All of that gets constrained. It fundamentally shapes who builds AI, who it's built for, and ultimately who reaps the rewards of this incredibly powerful technology.
So it's not just an environmental cost, it's a pretty significant societal one, too. It really does feel like we could be accidentally creating a future where only a few giants get to steer the ship on this transformative tech. But, okay, setting aside the costs for a moment, what about the performance? Isn't the whole point of these massive models that they do generalize better, that they perform well out in the messy real world?
Well, that brings us to the third limitation. And this one is really critical for actually using AI in the real world, these so-called real-world generalization failures. Despite their enormous size, despite being trained on these vast data sets, AI models built this way, often using massive but fundamentally static data sets, they frequently struggle. They struggle to generalize effectively when they encounter conditions that are novel or dynamic or just different from their training data.
So they're brittle.
In a way, yes. The paper talks about domain shifts. These are things like changes in lighting, background clutter, differences in sensor noise or blur, maybe even subtle changes in how a task is presented. These shifts are notoriously difficult for traditional, purely data-driven approaches. And while we have benchmarks trying to test for this robustness, the paper argues they often don't really capture the full complexity, the sheer messiness of real-world situations.
So the tests aren't realistic enough?
Often, no. And the result is that models trained really well on these benchmarks can suddenly show significant, sometimes really dramatic drops in performance when they're actually deployed. This obviously limits their reliability, their trustworthiness in really critical areas. Think about autonomous driving. A perception failure there could be catastrophic, or medical diagnostics where accuracy is absolutely vital. And the paper uses a great analogy. It's like training an Olympic swimmer, only in a perfect, still, temperature-controlled pool. No waves, no currents, nothing unpredictable.
Right.
And then you expect them to jump into the open ocean with choppy waves, cold water, maybe poor visibility, and still perform at that Olympic level.
They might be the best in the pool, but the ocean is a different game entirely.
Exactly. The real world is that choppy ocean. It's far less forgiving than the curated data sets these models often train on.
That analogy really nails it. You can have the biggest, most powerful engine, the largest model, but if it can't actually handle the varied, unpredictable, rude conditions of the real world, then a lot of that power is, wasted or maybe even dangerous.
Precisely. And this ties into the fourth limitation: economic sustainability and scalability. This relentless push for bigger models and more data creates a huge financial burden. It's not just the energy costs we talked about. It's the specialized hardware, high-end GPUs, TPUs, the infrastructure to house and run it, the cost of acquiring and labeling massive data sets, the highly skilled personnel.
It adds up fast, I imagine.
Extremely fast. These costs quickly become prohibitive for almost everyone except those few big players we mentioned. This economic barrier really hampers the wider adoption, the scalability of advanced AI. Smaller businesses, academic labs, organizations in resource-limited settings, they often just can't afford to play the scale-up game. It becomes like a treadmill of ever-increasing costs just to stay relevant. And finally, maybe most critically, we get to the ethical and societal concerns. These large-scale models, trained on vast swaths of internet data or other large data sets, inherently risk absorbing and even amplifying the biases present in that data.
Biases that reflect existing societal inequalities.
Exactly. And as these data sets grow to petabyte scale,
Right.
actually auditing them, finding these biases, and effectively mitigating them becomes incredibly difficult. It's like finding needles in continent-sized haystacks. So without really rigorous oversight and proactive strategies, which are hard to implement at that scale, these biases can easily propagate. They can perpetuate stereotypes, reinforce inequities, embed systemic prejudices in systems used for hiring, for loan applications, even for things like criminal justice risk assessment.
Which can cause real harm.
Immense harm. And it really forces us to ask that crucial question: can we genuinely fix these deep, complex ethical problems just by making the models even bigger? The paper argues pretty strongly that a purely model-centric view, focused solely on scale, is fundamentally inadequate for tackling these profound societal challenges. So yeah, all these limitations together, environmental, equity, robustness, economic, ethical, they really underscore this urgent need the paper identifies. We need to move beyond just scaling the model. We need strategies that integrate smarter, more adaptive sensing, more context-aware optimization right at the very beginning of the process, at the input stage.
Wow. Okay. That's a really comprehensive and, yeah, pretty sobering look at the downsides of the bigger is better path. Environmental unsustainability, widening inequity, failures in real-world generalization, prohibitive cost for most, and the risk of baking in and amplifying societal biases. That's a compelling list. A really urgent list of reasons to find a better way. So given all that, it could feel a bit discouraging. If just scaling up isn't the answer, where do we look? What's the alternative? Well, this is where the paper pivots to something really intriguing. It suggests we look at the original experts in perception, ourselves, and, the rest of the natural world. It brings in this fascinating idea that biological intelligence, our intelligence, is fundamentally embodied cognition. It's not just about brains and vats processing abstract data.
That's absolutely right. This is the core inspiration for adaptive sensing. The idea is that our brain, or any biological brain, isn't just this isolated computer chip crunching numbers. It doesn't operate in a vacuum. Instead, it's deeply integrated into a whole system. A system that includes our incredibly sophisticated sensory organs, eyes, ears, skin, sense of balance, sense of body position, working together with our muscles, our skeleton. And these components aren't just passive data collectors. They form these dynamic, crucial perception action loops. They're constantly interacting, constantly adjusting. And that's absolutely essential for how we survive, how we learn, how we evolve to thrive in a complex world. See, for truly effective perception, biological systems, humans, animals, they don't just passively soak up whatever information hits their sensors and then leave all the hard work to the brain. No, they dynamically adapt. They actively modulate their sensor parameters right at the source, both before the signal even gets processed deeply and during that processing. Think about your own experience. If your vision's blurry, maybe you need glasses, or the lighting's bad.
You don't try to somehow retrain your visual cortex to interpret thousands of blurry images better, right?
No, you put on glasses or turn on a light.
Exactly. You wear corrective lenses that shape the light before it hits your retina.
Yeah.
Or think about going from a dark room into bright sunlight, or trying to see details when it's really dim or hazy. What do you do instinctively?
You squint. Or maybe your pupils dilate in the dark.
Precisely. You squint. That rapid narrowing of the pupil, it sharpens your depth of field, it suppresses stray light, makes things clearer. The paper points out just how incredible this biological mechanism is. Our pupil diameter can change from maybe 2 millimeters up to 8 millimeters. That's like a 16-fold difference in how much light gets in.
Wow, 16 times.
And it can do that adjustment in less than 200 milliseconds. Super fast, super dynamic. Now, compare that to most artificial sensors, most cameras and AI systems. They typically have a fixed aperture or maybe a simple two-step adjustment. Nothing like that. Continuous, rapid biological adaptation.
That's an amazing comparison. It makes you realize just how much adaptation, how much optimization our own bodies are doing constantly, usually without us even noticing. It's just happening.
It really is. And it's not just vision. Take hearing. We humans have this incredible active gain control. Our ears can adapt to a stunning dynamic range of sound intensity over 120 decibels. That's largely thanks to these specialized cells, outer hair cells in the inner ear, that can actually amplify faint sounds or dampen loud ones. It's far, far beyond what typical MEMS microphones and devices can do. They usually top out around 60-90 dB dynamic range, often with just a fixed gain control.
So our ears are actively tuning themselves.
Actively tuning, yes. And more than that, our brain can send signals back to the ear in an efferent feedback loop to adjust sensitivity or even protect the ear from damaging loud noises. It's a proactive control that's mostly absent in artificial systems. Or think about touch. Our skin isn't uniform. It's got this mosaic of different receptors giving us this huge sensitivity range, from a super light touch like 0.3 kilopascals up to firm pressure over 500 kilopascals. Artificial tactile sensors, usually much narrower range, maybe 1 to 100 kpi. Plus, our skin is soft, it conforms to objects, and we have pain receptors, nociceptors, that trigger reflexes to prevent injury.
Right, if something's too hot or sharp, you pull away automatically.
Exactly. Artificial sensors are often rigid, and crucially, they lack that kind of pain feedback to protect themselves or the things they're interacting with.
Wow, it really sounds like our bodies are performing this constant, incredibly sophisticated real-time sensor optimization and self-protection that current AI hasn't even really started to replicate. We're always tuning our senses for the best possible input.
That's the core insight. The paper draws heavily on these biological examples to argue that true intelligence, robust intelligence, doesn't just come from having a complex neural network or a giant data set. Instead, it emerges from this coordinated evolution, this dynamic interplay between the sensors, the neural pathways, and adaptive behaviors. So this biological principle suggests that for AI to be truly effective, especially in the real world, it needs not just powerful processing, but also dynamic, real-time, proactive sensor adaptation throughout the whole perception process. And what's really striking when you look at it this way, it's just how static, how passive most artificial sensors are in comparison. They just capture whatever hits them, light, sound, pressure, without the sophisticated adjustments, the selective attention, the protective mechanisms that are just built into biological systems.
Okay, so we've really established the case. The current AI path has serious issues, and nature offers this incredibly powerful blueprint for doing perception way, way better. Now, let's connect those dots. What exactly is this adaptive sensing the paper is proposing? How does it bridge that gap between today's static AI sensors and nature's dynamic intelligence? Well, the paper defines it pretty clearly. Adaptive sensing isn't about passively receiving data. It's about proactively modulating sensor parameters. That means actively changing things, maybe exposure time on a camera, sensitivity on a microphone, maybe even how different types of sensors, like vision and touch, are configured and used together, and doing this right at the input level. So just to be really clear, it's not about trying to fix bad data after it's already in the AI model. It's about making the incoming data good, maybe even optimal, before it even hits the processing pipeline. It links directly back to that biological inspiration, right? It's about shaping the incoming photons or acoustic waves or tactile forces right at the sensor itself, like our eyes squinting or our ears adjusting gain. And the paper really emphasizes the potential here. It says this isn't just, an incremental improvement. It's potentially a critical paradigm level shift in how we build intelligent systems.
That's absolutely the heart of the argument. This isn't a small tweak. It's a fundamental rethink, shifting focus from solely processing data after it's collected to intelligently acquiring data in the first place. And what's really exciting is that there's already some strong early empirical evidence backing this up, especially coming out of image classification research. The paper introduces this prototype system called LENS. It's described as the first model-friendly test-time input adaptation framework. It's specifically designed to deal with those covariate shifts. We talked about changes in data distribution like blurriness, different lighting, things like that.
Okay, so how does LENS actually work?
It works by dynamically optimizing the sensor parameters, think camera settings, frame by frame, in real time. And crucially, it optimizes them to deliver data that is specifically model-friendly. This is a key point. It's not trying to make the image look beautiful or perfect to a human eye. It's trying to make it optimal for the specific AI model that's going to process it, tailoring the input to that model's internal workings and learned representations. And the results they got with LENS, they're pretty remarkable. They show adaptive sensing can significantly boost accuracy in some cases by up to an incredible 47.58 percentage points.
Wow, nearly 50% improvement.
Almost 50 percentage points, yeah. And importantly, this is achieved without changing the AI model itself at all, just by feeding it better data. Or, looking at it another way, adaptive sensing can allow a model to maintain its accuracy even if you drastically shrink its size, sometimes by as much as 50 times smaller.
50 times smaller, that's huge for efficiency.
It's enormous. But here's the example from the paper that really blows my mind, the one that really shows the potential scale of this shift. They found that with ideal sensor adaptation, a really lightweight model called EfficientNet B0, only 5 million parameters, which is tiny by today's standards, could actually outperform a massive model called OpenCLIP H. OpenCLIP has 632 million parameters, so over 120 times bigger, and it was trained on 160 times more data.
Wait, let me get this straight. A tiny model with the right sensor adaptation beat a monster model trained on vastly more data.
Exactly. A tiny model fed optimally adapted data by a smart sensor beat a behemoth model trained with brute force. Let that sink in for a second.
That completely flips the script on AI development.
It really does. It fundamentally changes the cost-benefit equation.
That's just incredible. It's like saying a tiny, well-aimed laser pointer can actually be more effective for seeing specific details than a giant, power-hungry floodlight if you tune that laser perfectly for the task. And it also brings up that really interesting, kind of counterintuitive point the paper made, that what counts as a good quality image for an AI model might be different from what looks good to us, to human perception. Can you elaborate on that? It feels a bit weird.
It's a great question. And yeah, it is one of the more surprising insights. We tend to assume, naturally, that if an image looks good to our eyes, nice exposure, balanced colors, sharp focus, say that then surely it must be optimal for an AI too. But the paper argues that what's high quality for our general-purpose human visual system, designed for navigating this incredibly complex world, might not be optimal for a specific AI model trained for a very narrow task, like classifying one particular type of object.
Okay, so the AI might want something different.
Potentially, yes. For instance, we might prefer a photo that looks natural, aesthetically pleasing. But an AI model, maybe one trained to be robust against certain types of noise or variations, might actually perform better with an image where specific features crucial for its classification task are exaggerated, or maybe where certain types of noise it's sensitive to are suppressed in a way that looks weird or even distorted to us. It might prefer an image that emphasizes texture over color, perhaps, or specific contrast levels over overall brightness in ways a human wouldn't prioritize. The lens system optimizes specifically for the AI's internal needs, its learned representations, not for human aesthetics. This implies that adaptive sensing really needs to be tailored. It has to be model-specific and scene-specific. It can't just be a generic, make-it-look-good approach. It kind of frees the AI from having to see the world exactly the way humans do. And beyond these striking early results showing raw accuracy gains, the paper argues that integrating adaptive sensing brings huge practical advantages for deploying AI in the real world. From a learning standpoint, think about it. The real world isn't like a clean simulation. It's messy, unpredictable. Sensors vary. Lighting changes, things get in the way. Adaptive sensing allows an AI agent to dynamically optimize its sensors on the fly, reducing this perceptual uncertainty. This targeted, intelligent data gathering leads to much more sample-efficient learning. The AI learns faster, with fewer examples. And it leads to more robust generalization, especially in complex situations where traditional methods often break down or where feedback is very limited. The AI learns smarter, not just bigger. Then there's the huge benefit for engineering and, crucially, economic viability. Adaptive sensing drastically cuts down on the computational requirements compared to just endlessly retraining massive models or constantly needing bigger data sets. By improving data quality right at the source, at the sensor, it lowers those immense costs for high-end GPUs, cloud compute infrastructure.
Which makes it more accessible.
Exactly. It makes advanced AI potentially much more feasible for resource-constrained settings, for embedded systems, maybe on your phone, or for smaller companies and startups that just can't afford the massive compute budgets. It's a potential game changer for democratizing AI, getting it out of the hands of only the giants. And critically, there's the potential for a really positive ethical and societal impact. By enabling this targeted, context-aware data collection, adaptive sensing could help mitigate those biases we talked about, the ones often baked into huge static data sets. If you're actively tuning your sensor to get the most relevant, least biased information for this specific situation, you're actively curating the input rather than just passively accepting potentially flawed, large data sets that reflect historical inequities.
So it could lead to fairer outcomes.
Potentially, yes. Fairer, more equitable outcomes in sensitive areas, maybe enhancing public trust. Imagine, say, a medical AI dynamically adapting its sensing for this specific patient, rather than relying solely on a general model that might underperform for certain demographic groups present in the training data. And finally, this whole approach, being inspired by biology, naturally encourages interdisciplinary work. It brings together computer scientists, engineers, ethicists, neuroscientists, policymakers. It pushes for more holistic solutions that think about performance, sure, but also sustainability, ethics, societal well-being. So, yeah, in summary, the paper makes a really compelling case that adaptive sensing is this necessary paradigm shift towards AI that's smaller, greener, fairer, and ultimately just more effective in the real world. It elegantly turns that idea of sense better into learn less.
Sense better, learn less. I like that. It's such a concise and powerful way to frame this whole shift. It really redirects the effort, doesn't it? Away from just brute force computation towards more intelligent, more refined data gathering. So, okay, given all these advantages, environmental, ethical, performance, where can we actually expect to see this smarter sensings make a real difference? Like moving beyond the lab examples, what are the tangible, practical applications where this could really change things? Because that's where it gets really exciting, thinking about the real world impact.
Absolutely. This is where the vision really comes alive. The paper outlines several concrete scenarios across different fields where adaptive sensing could be truly transformative, especially as AI moves more and more out of simulations and into physical robots and devices interacting with our messy, unpredictable world. First, let's think about humanoid robotics. Imagine a robot trying to navigate a cluttered room, or pick up something delicate like an egg, or interact safely with people. Adaptive sensing would allow this robot to dynamically adjust its vision, its hearing, its sense of touch, all in real time. This could dramatically improve its balance when walking on uneven ground, or refine how it manipulates objects, knowing exactly how much force to use for something fragile versus something heavy. It could make its interactions much smoother, more natural, safer. For instance, a robot could literally adjust its fingertip pressure sensitivity based on the texture and weight it senses, rather than just using a fixed, pre-programmed grip force.
Like we do instinctively, we don't consciously think about how hard to grip a paper cup versus a heavy mug.
Precisely. We just do it. Adaptive sensing could give robots that kind of intuitive physical control. That would be a massive leap in making them more versatile and safer to have around in homes or workplaces.
Yeah, that makes total sense. A robot that can feel its way appropriately is much more useful. What about other areas?
Okay. How about healthcare diagnostics? This is a huge one. Adaptive sensing could revolutionize how we capture medical images. It could allow for dynamic adjustment of parameters during an MRI scan or an X-ray or an ultrasound, optimizing the image quality based on the specific patient's anatomy or the clinical question being asked.
So clearer scans tailored to the individual.
Exactly. Imagine dynamically adjusting an MRI sequence to get a clearer view of a specific type of tissue anomaly, or changing X-ray settings based on a patient's body density to reduce noise. The result: clearer, more informative images for doctors. That means potentially much higher diagnostic accuracy, leading to earlier detection and better treatment planning. It's about getting much higher quality patient-specific data for the experts to interpret. Then there's autonomous vehicles. Here, adaptive sensing is directly linked to safety, which is paramount. Think about a self-driving car encountering sudden changes, driving into a dark tunnel, emerging into bright sunlight, hitting dense fog or heavy rain or snow.
Yeah, conditions change fast on the road.
Very fast. Adaptive sensing would let the vehicle optimize its sensors, its cameras, its LiDAR, its radar in real time to cope with these changes. Maybe it automatically adjusts camera exposure, changes the LiDAR pulse pattern, tweaks the radar gain, all specifically to handle fog or rain or glare. The goal is to keep the vehicle's perception reliable no matter what the environment throws at it. This is absolutely critical for safety.
Critical is right. If the car can't see reliably, it can't drive safely. That's a massive potential benefit.
Huge.
Now,
Okay, let's shift gears to agriculture monitoring. Think about drones flying over fields. An adaptive sensing drone could dynamically adjust its camera settings, exposure, focus, maybe even the spectral bands it's capturing based on what it's seeing. Maybe it adjusts differently for different crop types or different growth stages or signs of stress like drought or pests.
so it gets better data depending on the situation.
Precisely. It optimizes in real time for precise crop health monitoring. This gives farmers much more accurate, actionable information to manage their fields, optimize water use, maybe apply pesticides more targetedly. Imagine it automatically adjusting for the shade under dense leaves versus the bright sun on young sprouts.
And one more, environmental monitoring. Similar idea. Adaptive sensors could optimize their settings dynamically to get more accurate data on air or water quality, even when conditions are changing, high humidity, fluctuating temperatures, different kinds of pollutants. This could lead to much more reliable pollution tracking, better climate modeling. And this capability, this dynamic adaptation, it becomes really critical as AI moves out of the lab. Because in the real world, AI systems will get data from all sorts of different sensors, different brands, different firmware versions, maybe even slight differences between batches from the same factory.
So even subtle hardware differences create challenges. They create these subtle but significant domain shifts that are really hard to handle just by making the AI model bigger. Adaptive sensing offers that crucial complementary piece for achieving true, real-world robustness. It handles the variations at the source.
Those examples really drive it home. Humanoid robots, healthcare, self-driving cars, agriculture, environmental monitoring. It touches so many vital areas. It's clearly not just some abstract idea. It has profound practical implications.
Yeah.
Okay, so let's go a bit deeper now. How does this actually work, especially for AI that needs to physically move and interact, for what the paper calls embodied AI? You mentioned current embodied AI often focuses just on action-centric training, learning the movements without explicitly considering adaptive sensing, and that leads to problems with efficiency and adaptability in the real world.
Right, this is where we get into the mechanics of making adaptive sensing work, not just for static perception, but for dynamic interactive intelligence. The paper uses a great analogy, which is in Figure 2a, a child learning to balance. It perfectly illustrates how we humans seamlessly weave together sensory adaptation and motor actions. It's a continuous closed loop. Think about walking on tricky ground ice, rocks, a steep hill. We don't just mechanically change our steps. We instinctively, simultaneously adjust our sensory inputs. Maybe we become more sensitive to pressure changes in our feet. Maybe we rely more on our inner ear for balance.
And then we adjust our movements.
Exactly. We modulate the sensor gains and adjust our actions, like stride length or foot angle. Perception and action adapt together, constantly informing each other. And humans get good at this remarkably quickly through this efficient, tight feedback loop, often needing just a few tries. Current embodied AI agents, the ones mostly just optimizing actions. They lag way behind in both how fast they learn and how robust they are when faced with these kinds of dynamic, real-world challenges. They're essentially trying to balance with their eyes half closed, metaphorically speaking. So what are the gaps in the current approaches?
Well, most adaptive sensing methods we've seen so far, like that lens prototype, they're mostly designed for single-shot perception, like taking one perfect photo. They don't really address continuous interaction, sequential decisions, where the world keeps changing and the AI needs to keep adjusting.
So they miss the ongoing loop. They miss the crucial role of that ongoing closed-loop feedback between sensing, perception, and action. That continuous dialogue is essential for embodied agents. Also, current methods often don't actively use feedback from the AI model's perception to guide how the sensor parameters are explored. This is a big limitation, especially when rewards are sparse, when the AI only finds out it succeeded much later. You need efficient exploration guided by perception quality. It's about learning how to look, not just looking.
Okay, so it's not just about perceiving better now, but about the AI actively learning how to perceive better over time, in real time, and connecting that directly to its physical actions. That sounds like a much more active, much more intelligent role for sensing itself.
Precisely. And to bridge these gaps, the paper proposes a more principled adaptive sensing framework specifically for embodied AI. Let's try to break down the progression it suggests, simplifying a bit. First, you have the basic single-shot adaptive sensing. This is mostly perception only, like our lens example shown in Figure 3b. Here, the AI might try out, say, K different sensor settings. Imagine taking K photos of a scene with slightly different exposures or focus points. It then evaluates how good each resulting measurement is from the model's perspective, using some perception-aware quality metric, maybe how confident the model is in its classification based on that specific image. Then it picks the best setting from those K options. It's like programmatically choosing the photo the AI can understand best, even if it doesn't look prettiest to us. It's the first step toward intelligent data acquisition. Next, they generalize this to single-modal continuous perception tasks, which is in Figure 3c. Now we're in a sequential setting, but still mostly just perception, no physical action yet. Think of a robot just watching something move.
At each moment, it decides how to best adjust its sensor, say its camera zoom or focus, to keep tracking it clearly. The paper draws inspiration from how babies learn to control their gaze, focusing on what's important. Here, the AI sensing policy actively tries to maximize that model-centric quality score over time. It learns to continuously tune its perception for optimal clarity. Okay, now for the core of embodied AI. Continuous sensor motor tasks, shown in Figure 3rd. This is where sensing and action truly come together. The robot is moving, interacting. At each step, the agent looks at its state, and then it jointly decides on its next physical action and its next best sensor configuration. They're chosen together.
So it's deciding how to move and how to sense simultaneously.
Exactly. And the crucial part is the reward signal.
Mm-hmm.
The paper suggests modifying the reward function. The robot isn't just rewarded for completing the task, like walking across the room. It's also rewarded for how well it was sensing during the task. So it gets a combined reward. Mm-hmm. Abstractly, you can think of it like R task plus lambda QM. R task is the reward for doing the physical thing. QM is the quality of its sensory input, and lambda is just a weight balancing the two. This joint reward encourages the robot to learn efficient integrated policies for both sensing and acting. It learns to move well and see well together.
So it's incentivized not just to succeed eventually, but to succeed smartly by actively managing its senses. That feels like a big departure from just rewarding the final outcome.
It's a huge conceptual shift.
Yeah.
And it gets even more sophisticated with adaptation to multimodality settings. Robots usually have multiple senses, vision, touch, maybe hearing. Here, the agent learns to dynamically allocate its attention and resources across these different senses, depending on the context. Think about us again. If you're standing still, maybe pressure sensors in your feet are key for balance. But if someone pushes you sideways, suddenly your ankle proprioceptor sensing joint angles become much more important.
Right. You shift focus depending on the situation.
Exactly. We do this instinctively. The paper proposes mechanisms, like a modality weight vector, that let the AI agent dynamically focus its sensing resources on whichever modality is most informative right now. So a robot might rely heavily on vision when navigating an open space, but switch to prioritizing tactile feedback when it's trying to manipulate something small or in the dark. And finally, they tackle humanoid-scale multimodal tasks under sparse rewards. These are the really tricky ones, like a robot trying to open a bottle cap. Often the only reward is binary and sparse. Did the cap come off? Success or not? Failure. The robot gets very little guidance along the way. Learning from that is incredibly slow.
Yeah, how does it know why it failed?
Right. So the solution proposed is to introduce intermediate, perception-aware, continuous sensing quality metrics. Let's call them key. These metrics can quantify intermediate progress or maybe provide cross-modal feedback. They give the robot much richer, denser guidance during the task attempt. For example, imagine the robot is trying to screw on the cap. Its vision might be a bit uncertain about alignment, but its tactile sensors might provide feedback. Grip feels tight, threads seem engaged. This positive tactile feedback, Q grip, could actually boost or refine the visual quality metric, QVs, giving the robot more confidence to proceed. The senses help each other out.
So instead of just a final pass-fail, the robot gets this constant stream of, how am I doing? Feedback from all its relevant senses, guiding it step by step. That sounds much more informative for learning.
Exactly. These detailed multimodal quality metrics get integrated into a more complex reward function, maybe something like RTH R sparse plus lambda tac Q grip plus lambdatus QVs. So the robot gets reward not just for the final success, R sparse, but also continuous rewards based on how well it's sensing with touch, Q grip, and vision QVs throughout the process, guided by the respective sensor configurations. By using these intermediate modality-specific metrics, the agent gets this rich continuous feedback stream, which really helps overcome the huge challenge of sparse rewards in traditional reinforcement learning. And connecting this back to the bigger picture, these kinds of closed-loop adaptive sensor motor systems are absolutely fundamental for creating truly intelligent, truly robust, truly adaptable robots that can actually function effectively out in the complex, messy, unpredictable real world. It's how we move beyond robots that only work in highly controlled labs.
Okay, it's definitely clear that adaptive sensing, especially when you integrate it into these sophisticated closed-loop systems for embodied AI, represents a massive potential leap forward. But, as with any major shift, any true paradigm change, it's not going to be easy. This sounds amazing, maybe even a bit futuristic, but fundamentally changing how an entire field like AI operates that comes with hurdles. So what does this mean for the near future? What are the real roadblocks, the practical and theoretical challenges that need to be overcome for adaptive sensing to move from being a promising research idea to becoming, the new standard?
You're absolutely right to ask that. The path forward definitely isn't smooth. The paper itself is quite critical in assessing the hurdles. It lays out several key challenges, technical, infrastructural, even ethical, that need serious attention before adaptive sensing can really take off. First, there's a big lag of standardized benchmarks. The tests we currently use to compare AI models, well, they rarely capture the kind of dynamic sensor variations in changing environments that adaptive sensing is designed to handle. And the few adaptive sensing benchmarks that do exist, they're often quite narrow, mostly focused on simple image classification. This makes it hard to really compare different approaches broadly or know how well they'll generalize to other tasks or domains. It's tough to prove something's better if you don't have the right measuring stick. Second, there's this issue of unspecified objectives. How do you define good sensing for an AI? Current strategies often rely on fairly simple proxies, like how confident the model is in its prediction, or measures of whether the data looks out of distribution. But the paper argues these simple metrics often don't really capture the true quality or usefulness of the data for the model, especially dealing with those complex real-world shifts. We need more sophisticated ways to quantify what optimal sensing actually means in a dynamic context. Concepts from statistics like Aleatoric uncertainty, the inherent noise in the data, and epistemic uncertainty, the model's own uncertainty about its knowledge, these might be crucial. We need metrics that reflect these deeper types of uncertainty to guide sensing decisions more effectively.
Okay, so we need better benchmarks to measure progress and better definitions of what we're even trying to optimize for when we talk about sensing quality. It sounds like the very fundamentals need refinement.
Exactly. A third big challenge is the sheer complexity of multimodal sensor spaces. Once you start trying to coordinate multiple senses, vision, touch, hearing, maybe proprioception, the number of possible ways to configure and combine them just explodes. This massively increases the size of the perceptual space the AI has to search through and the solution space for finding the best sensing strategy. It makes the learning problem much harder, especially if rewards are sparse or delayed, like in that bottle cap example. Just managing the combinatorial explosion is tricky. Fourth, and this is a really practical one, there are likely performance trade-offs, at least initially. Early adaptive sensing systems might not immediately hit the absolute peak performance numbers that we see from today's giant resource-guzzling models trained on massive data sets.
So they might be more efficient, more robust, but maybe not top the leaderboards right away.
Potentially, yes, and that's a significant hurdle for adoption. Decision makers, whether in industry or research, often prioritize that immediate maximum accuracy score, even if it comes at a high cost in terms of sustainability or real-world reliability. It can be hard to convince people to switch paradigms if the initial benchmark numbers aren't immediately superior. Then there are the integration barriers with existing frameworks. Let's be realistic. Implementing adaptive sensing isn't just adding a small module. It often requires fundamental changes to existing AI pipelines, the software stacks people use, maybe even the hardware platforms. That represents a huge logistical challenge, a significant economic investment, and just organizational inertia for a field that's already heavily invested in the current model-centric way of doing things. And finally, looping back to something we touched on earlier, there are very real ethical and privacy concerns. If you have sensors that are actively, dynamically optimizing themselves in real time based on the context, they might inadvertently become much better at capturing sensitive information.
Like facial recognition or picking up private conversations.
Exactly. An adaptively tuned camera might capture biometric data more effectively, even if that wasn't the goal. A microphone optimizing for one sound might become better at isolating background conversations. This is especially worrying in sensitive environments, public spaces, homes, hospitals. So it forces us to ask, how do we build these more perceptive systems without creating new privacy risks or worsening existing surveillance issues? That needs a very careful, proactive consideration.
Those are definitely significant hurdles. They span the whole spectrum from fundamental research questions about metrics and benchmarks to engineering challenges, economic viability, and deep ethical considerations. So acknowledging all that, what's the path forward? What solutions or research directions does the paper suggest to tackle these challenges and help adaptive sensing realize its potential?
The paper doesn't just point out problems. It does propose several key strategic directions, emphasizing collaboration. First, as we discussed, is developing standardized benchmarks. We urgently need comprehensive, realistic tests that evaluate dynamic sensor adaptation across diverse tasks, environments, and sensor types, not just image classification. This also includes creating better synthetic simulations grounded in real-world data to allow for fair and controlled comparisons. Second, a major research push is needed for better data quality metrics. We need to move beyond simple confidence scores and develop metrics that truly capture the model's perception of data quality under real-world shifts, perhaps incorporating those ideas of aleatoric and epistemic uncertainty we mentioned. These metrics are crucial for guiding the adaptation process effectively. Third, we need ongoing algorithmic innovation in real-time adaptation. This means more research into efficient algorithms, drawing from reinforcement learning, adaptive control theory, online learning, all tailored for rapidly optimizing sensor parameters in dynamic, unpredictable situations.
We need faster, smarter ways to explore that complex sensor configuration space. Fourth, the paper really stresses the co-development of models and sensor strategies. Stop developing the AI model and the sensors in separate silos. We need integrated approaches that optimize the AI architecture and the adaptive sensor parameters together, letting them inform each other for better overall robustness and generalization. Think co-design from the start. Fifth is the exciting area of multimodal and language-driven adaptive sensing. The idea is to use language commands or broader context to guide sensor adaptation. Imagine telling a robot, find the smallest red block, and it uses that instruction to adaptively tune its vision for color and size, maybe engaging touch to confirm. This could lead to much more natural human-AI interaction and unlock applications in robotics, healthcare, and more. And finally, directly tackling the ethical issues, there's a critical need for privacy-preserving sensor optimization. This means developing methods that are secure, maybe run efficiently on the device itself, on device AI, to avoid sending sensitive raw sensor data elsewhere, and are explicitly designed with privacy safeguards built in. This area in particular absolutely requires deep, ongoing collaboration between AI researchers, ethicists, legal experts, and policymakers to ensure these powerful new capabilities are developed and deployed responsibly, maintaining public trust. The paper really hammers home that this whole endeavor needs to be collaborative and interdisciplinary. No single group or field can solve all these challenges alone. It requires a broad, concerted effort.
That's a really clear and comprehensive roadmap. It acknowledges the challenges, but also lays out concrete steps for moving forward towards what feels like a potentially transformative new era for AI. So we've taken a real deep dive today. We've explored why just making AI models bigger and bigger, the scale bigger approach, is running into some serious walls, environmental, economic, ethical, and even performance limits in the real world. And we've examined this compelling alternative paradigm, sense better, not just scale bigger. Inspired by the incredible dynamic adaptability of biological senses, adaptive sensing offers this path towards AI that could be not just more powerful and robust when facing the complexities of reality, but also significantly more sustainable, more equitable, and fundamentally more responsible. It's really about shifting the focus, right, towards being smarter, more intentional, more efficient about how AI gathers information in the first place, which counterintuitively perhaps might mean it can ultimately learn more effectively and reliably, using less data and far less computational power. So as you go about your day, maybe mull this over. If we could genuinely make AI systems smarter by teaching them to sense and perceive the world with more adaptability, more precision, instead of just making them bigger through brute force, what entirely new possibilities might that unlock? For technology, for science, for how we live, and what new ethical questions arise when AI becomes not just computationally intelligent, but perceptually adept, truly embodied, capable of actively tuning its own senses? Could really digging into and understanding our own amazing human ability to dynamically adapt our senses, squinting in the sun, cupping an ear to hear better, subtly adjusting our grip, could that understanding unlock the next big frontier for AI? Maybe something beyond what we can even currently imagine. Thank you for joining us on this deep dive into the fascinating world of adaptive sensing. We hope it's given you some fresh perspectives on the future of artificial intelligence. Until next time.